Hi, welcome to the Signal Path. In this episode, I wanted to investigate the effect of extreme low temperatures on some of the electronic components that we use all the time. So I have prepared a group of components that we're going to expose to really low temperatures in liquid nitrogen, and we're going to study their behavior. First, we're going to look at what theoretically is supposed to happen, and then we're going to do the experiment itself and then compare our results with the theory predictions. So to tell you a little bit about liquid nitrogen, I have a Dewar here that's full of it. Is a colorless, odorless liquid that's just a little bit lighter than water, and it boils at minus 196 degrees Celsius at atmospheric pressure. It's usually manufactured by partial distillation of liquid air, and liquid air itself is manufactured by compression and then taking the heat away until it brings it down to room temperature, and then the pressure is dropped and the liquid cools down. But it is not something that you should play around with unless you're very familiar with it. Not only poses, of course, a serious frostbite damage because it is so cold, you shouldn't also pour it into containers that are not designed to handle it, because the thermal shock can actually shatter whatever container that you pour it in, and then those pieces can fly off and can be dangerous. Also, you should never pour it in something that's completely closed, because the pressure will build up, and then again, if the container is not designed for it, it will explode, and it can be very, very dangerous. Also, if you're in a small room and you pour a lot of liquid nitrogen, it will begin to replace the air that you're breathing. And since you can't breathe nitrogen, eventually there's not enough oxygen left in the room, and it can be very, very dangerous and can be fatal. So make sure you really understand how to use liquid nitrogen. Always wear gloves and have goggles on to protect yourself against possible damage. But there's also one other thing. I wanted us to be able to see whatever it is that I'm putting inside liquid nitrogen. So I bought something really interesting. Let me show you. So liquid nitrogen is typically kept in Dewars, like the big white one that I showed you earlier that had the entire liquid nitrogen in it. But when I went ahead and I bought a glass Dewar from eBay for about $40 or $50 including shipping, which I consider to be a very good deal. So this glass container is not only thermally protected, so you can pour liquid nitrogen in it without it breaking, but it's also two layers, just like Dewars should be. There is an inner layer. The inner tube itself is where the liquid nitrogen will be poured into, and the outer layer is protected from the inside via a layer of vacuum. So there is nothing that they use this little knob here. They can see that this was molten. They suck the air out of it and then they melt the glass to close it up. Usually Dewars have one layer that is mirrored so that you can prevent heat from entering or exiting due to radiation, but they've omitted that layer of mirroring here because they want to be able to see what's inside it, so that when we put something inside and I fill this with liquid nitrogen, we can see the component. It's more interesting, and also if you're doing an optical experiment or something where you need to see the device under test in liquid nitrogen, this is the only way to do it. So it's not a very good Dewar, but for our purposes it's perfect. Also, one other thing that this Dewar can do is that it can also withstand quite a bit of pressure, so you can create a vacuum in here and do some other experiments, which we are not going to do in this video. So as our first component to test, let's try a very simple resistor. We know that resistor's conductivity is given by this expression, and this expression is a function of delta T, which is a change in temperature. So if T goes down, the delta T will be negative. As a result, the conductivity will go up. As a result, the resistance will go down. So if I reduce the temperature, I expect the resistance to go down. But not every resistor is going to behave the same way. It depends on the property of the material. So I've chosen 3 different resistors here that I've mounted on these sticks. So all these experiments are going to use a similar setup, but I have mounted a component at the end of the stick, and we're going to put it directly into the Dewar and then measure the change in the behavior. So I have a very old resistor here. I don't know if some of you may have seen this type of really, really old resistors. Let me see if I can get a better view here, like this. So this type, this is a carbon compound resistor that has a very poor temperature behavior, temperature stability. So we're going to measure that. And I have this modern type resistors with which you must have used a lot. And then I have this type of resistor, which is a thin carbon film resistor that's supposed to have very good temperature coefficient and temperature properties. So let's measure these resistors at room temperature, write the resistance value in here at T equal to 25 degrees Celsius, and then we're going to measure them again at minus 195 degrees Celsius, and then let's see how much the resistance changes as a total percentage and also as an absolute delta. So let's get started and let's do that. So here I have the setup. I have put the Dewar here, so the Dewar is sitting here right now, it's empty, and I have the multimeter and the power supply connectors up here. So I'm going to connect them one at a time, and I'm going to write them down. Okay, I'm connecting it to the meter. So at room temperature, our old resistor has a total resistance of 13.1 kilo ohm. So I'm going to write that down. 13.1 kilo ohm. You can see that I'm just connecting them up here. Let's disconnect this one. The second resistor, the more modern version of the same material, I have a resistance of, oops, that is not the right wire to connect this to. I have too many things here. Here we go. That is 9.98, so I've chosen them all to be pretty close to each other in terms of resistance. So 9 points, so I'm just going to put this at 10K. And finally, the thin film resistor that's supposed to have very good temperature coefficient and good resistance stability as a function of temperature should have about the same value also at room temperature. Yep, 9.5 kilo ohm. Okay, here we go. 9.5K. So now we can pour some liquid nitrogen in the Dewar and start putting these resistors inside. So to do that, I have a little funnel. Okay, so there's a liquid nitrogen inside the Dewar. It will of course be boiling for some time until the inside of the Dewar reaches room temperature. Now the outside of the Dewar will begin, unfortunately, to condense despite the fact that there is already very good thermal protection from the outside, but it will nonetheless have some condensation that will happen. So let's connect the old resistor if I can find it. And let's see the change in the resistance. So the resistance was 13.1 kilo ohm, and I'm going to, hear this, I'm going to put it inside the Dewar. I'm going to get a relative measurement. So I click on that, so now it says 0, and I'm dropping it in the liquid nitrogen. Let's see what happens. There we go. So it changed by 8 kilo ohm, which is a huge value considering that its actual resistance was 13.1K. So the delta R is 8.3K. Write that down. And if I remove the relative measurement, you can see that its resistance went up all the way to 21.5 kilo ohm. So we write that down. Okay, so that was the first resistor. Let's switch it up. Put this one out. The second resistor at room temperature was about 10K. There we go. You can see that it is at 10K. I will put it in relative mode again. I'm going to put that in. Like this. It's inside liquid nitrogen now. This one changed by 800 ohms, which is a factor of 10 better than the resistance I just measured. That is a big difference. So it's about 10 times better, 10 times more stable versus temperature. 800 ohms. If I remove the relative measurement, its value is now 10.8K. Alright, now finally the last resistor. This is the thin film carbon resistor that's supposed to have very good temperature stability. So its value is 9.5K. I'm going to put it into relative mode again. I'm going to put this in liquid nitrogen. Like this. Oops, sorry, the wires were shorted. There you go. Now this one changed by only 82 ohms. Again, another factor of 10 improvement. So the actual resistance therefore is 9.59 kilo. Okay, so let me do some calculations to find the percentage change, and then we'll look at the results. So here's all the results tallied up. So you can see that the delta R was 8.3K, 800 ohms, and 82 ohms. So the first resistor changed by 63% when its temperature dropped by about 200 degrees Celsius. The second one 8%, and the last one only 0.8% change in resistance for a temperature change of 200 degrees or 220 degrees. So it's very important. You can see the importance of using different types of resistor in your design. Not everybody cares about such large temperature changes, but if you need something accurate as a function of temperature, you know what to go for. So for our next experiment, let's look at an electromagnet. So electromagnet is nothing more than an inductor or a coil that has some internal resistance associated with it. This resistance is the resistance of the wire used to make up the coil. Now we know from Maxwell's equations that if you pass current through an inductor, there will be a magnetic field that's created around it. You can find the strength of that magnetic field, B, by doing a closed loop integral through the length of the wire with the permeability and the current that's through it. Now for a solenoid, which is a coil wrapped around multiple times, you can do some calculation, some simplification, and calculate the strength of the magnetic field B to be the permeability mu times N, which is the number of turns, and I. So right away we know that if I want to make the magnetic field stronger, I have to increase I have to put more and more current through it. That makes sense. You put more current through something, you burn more power, so then you're going to get more magnetic field out of it. But if you look at the solenoid itself, the current that you can put through a solenoid depends on its internal resistance and the voltage that you put across it. So the current is just V divided by R, which is essentially Ohm's law. Here, therefore, if I were to reduce temperature, I can reduce the resistor, as we've seen before, because you reduce the resistor of the conductor. That means the current will go up. That means the magnetic field would get stronger. So at the same power consumption, if I were to cool a coil, I will be able to get more magnetic field out of it. So I have prepared an experiment for that. I have attached a little solenoid, such as this one, that is at the end of this stick, like the previous experiment, where I can measure the resistance and I will measure the magnetic field that is produced by this coil, and I'll show you how to do that in just a second. I got this coil from inside a relay that was rated for 24 volts. You can see it says 24 volts on it. So what we're going to do is we're going to put 1 watt through it. So I have here in this table power of 1 watt. So at the same power consumption, we will measure the magnetic field at 25 degrees Celsius and at a minus 195 degrees Celsius inside the liquid nitrogen. So we can see what kind of magnetic field we can get by cooling the coil itself. To measure the magnetic field, I'll be using this Hall effect sensor that's connected to this cable right here. So this Hall effect sensor is mounted at the tip of this sensor here, which I'm going to connect to a Lakeshore 410 Gauss meter. So by using this instrument in conjunction with the sensor, we should be able to measure the exact magnetic field. So I'm going to set it up so you can take a look. So here's our setup for measuring the magnetic field of the solenoid. I have placed the solenoid inside the Dewar, but I've also added the Hall effect sensor right underneath the Dewar in order to measure the magnetic field, which goes through, of course, the glass and the Dewar. So right now there is no current through the solenoid at all. I'm measuring its DC resistance. So let me give you a close-up view of what's going on. So here is the solenoid inside liquid nitrogen with the Hall effect sensor right nearby. The outputs are taken from the top, and I'm measuring the DC resistance at room temperature of the solenoid, which is 475 ohms. And I have also the power supply down here. I can change the wires to the power supply to put some current through it and to be able to measure the magnetic field. Right now, since there is essentially no current through the coil, I'm seeing no magnetic field at all. That 0.01 is just a spurious value. So I'm reading right now 0.02 milliteslas coming out of the instrument, which is the null. We have to null that out. We're only doing relative measurements anyway. So let me put this guy back. I have already written down the DC resistance, which we saw. There it is, 475 ohms. I've written 480 ohms on the piece of paper, so we can then compare results. I'm going to switch the connections to the power supply so we can put some current through the solenoid. There we go. And that's that. So I've made the connections. So let's look here at these two numbers. I'm going to increase the voltage. I'm going to turn the power supply on. Right now it's set to 0 volts, so there's no current. I'm going to increase the voltage of the power supply until I see exactly 1 watt of power dissipated in the coil. There we go. That should about do it, maybe a little bit less. There you go, exactly 1 watt. So right now there is 1 watt of power in the solenoid, which happens to be 45 milliamps, and I'm applying 22 volts. So they can do the Ohm's law calculation based on the 480 ohms of resistance. We can see that number makes sense, and I'm reading 0.22 milliteslas of magnetic field being generated. This is all at room temperature. So what I can do now, I've written down, let me write down in the paper also the magnetic field. I'm going to write 0.22. There you go. So now we have taken a record of the strength of the magnetic field at room temperature at exactly 1 watt. You can see the power starts to drop. That's because the coil is heating up, its resistance is going up, so the current goes down. But I wanted to know at exactly room temperature, so the first number that we measured was the number that I was interested in. So I'm going to add some liquid nitrogen to this now. First, let me turn this off. I'm going to connect this back to the multimeter so we can see the resistance as the temperature rapidly drops. There we go. Now the resistance is 507 ohms. As I told you, the reason it went up is because the coil heated up due to the current that I put through it. So here we go. Let's connect it. Let's pour some liquid nitrogen in here. And since nothing has moved and everything is going to be exactly the way it is, I can do a relative magnetic field measurements afterwards. Add some liquid nitrogen. Just enough to have the coil sit directly inside it. There we go. Let me take this out so we can take a closer look at the coil. So it's boiling in liquid nitrogen. That's of course because it's it's about 220 degrees or so warmer than liquid nitrogen itself. And as it slowly begins to reach the temperature of liquid nitrogen, the boiling will slow down and eventually stop. So let's look at the resistance. It has already dropped to less than 200 ohms. Remember, we started with 480, but this is going to continue to go down. So we're going to wait a little bit until the temperature stabilizes, reach minus 195 degrees Celsius, and we will find out what the resistance is under that condition. Okay, so the resistance has pretty much stable now at 59 ohms. So it went from 480 to 59, almost a factor of 10 reduction. Now I want to point out that this is not superconductivity for two reasons. A, it's not cold enough. In order for superconductivity to start becoming an issue, you have to look at temperatures below 4 Kelvin. So liquid helium would have to be used. And also copper, it doesn't achieve superconductivity in the first place. It's not one of the metals that can do that. So, and you can see that there's a little bit of condensation on the outside right now because, again, there's too much humidity in the room. So now that we have the DC resistance at 59 ohms, let's do the magnetic field experiment, doing the same thing, increasing the voltage until I see exactly 1 watt. So let me change the wires up. Alright, here we go. I have now connected it back to the power supply. I will set the voltage back to 0 volts and I will turn it on. So now we have again no current, so let me increase the voltage again. And 2 volts, there we go. 5 volts, 8 volts, 8 volts. So now I'm applying 8 volts. Before I was applying 24. And before I used to get 50 milliamps, now I'm getting 131 milliamp. But I'm burning the same amount of power. I am burning exactly 1 watt as I was before. You can see the power is starting to drop very rapidly because the coil is heating up. But the first measurement that we took was the one that I'm going to record. We had a resistance of 59 ohms. I'm going to write that down. 59 ohms. And I also read 61 milliteslas as the magnetic field. And that was at 134 milliamps. Oops. Well, I wrote this in the wrong place, but anyhow. So let's look at the results here. So what did we get? The measurements showed that at room temperature we had 480 ohms, and at minus 195 degrees, I wrote it here by mistake, at minus 195 degrees Celsius we went down from 480 ohms to 59 ohms, and the magnetic field went from 0.22 milliteslas to 61 milliteslas at comparing 50 milliamps to 134 milliamps. So this principle essentially means that I managed to produce a much stronger magnetic field at the same power consumption, or I could have produced the same magnetic field at much lower power. This is not magic, of course. We're not breaking laws of thermodynamics, because the difference in the power consumption, the difference in the energy, comes from the fact that a lot of energy was used to produce the liquid nitrogen in the first place in order to compress it and to distill it to become into liquid form. So that's why this difference is there. And this is a principle used in particle accelerators and MRI machines to cool the coils down in order to be able to produce stronger magnetic fields at a reasonable power consumption. For the next experiment, let's move away from passive devices and look at some active devices. Specifically, let's look at a p-n junction, which is essentially the junction between a p-type semiconductor material and an n-type semiconductor material. And when you create this type of junction, you create a diode, which you've seen, of course, and used before. Now, the current through a diode depends on the voltage across it, but the relationship is exponential, and it's given by this equation, where I, the current through the diode, is a function of V, which is the voltage across it, and it's also a function of other constants such as Is, N, which is a linearity, ideality factor of the diode, and so on. You can approximate this equation to just be Is times E, the power of V over Vt. Vt is the thermal voltage. So you can see as V increases, I is going to increase exponentially as a function of V. But you can also reverse this equation and calculate the voltage across the diode as a function of the current through it. So that would be a log-based relationship, the opposite of the exponential, which would be NVT, N is usually 1, NVT ln of I over Is. Now Vt itself is kT over Q, where K is Boltzmann's constant, T is temperature, and Q is the charge of an electron. So you can see Vt is a function of temperature, but it also happens that Is is also a function of temperature, and Is is a much stronger function of temperature and Vt is. So even though Vt is a function of temperature, Is is a much stronger function of temperature. As a result, when temperature drops, Vt drops, but Is increases much faster. So as a result, V will go up. So at a constant current, when you reduce the temperature, the voltage of the p-n junction will go up and not down. And you can calculate, depending on the material property, that's about 2 millivolts per degree Celsius. So every time the temperature drops by 1 degree Celsius, the junction voltage will go up by 2 millivolt as well. So we can measure this. We can measure at a constant current of 1 milliamp, we can put 1 milliamp through a diode, find the voltage at temperature of 25 degrees Celsius, and find the junction voltage at a temperature of 195 degrees Celsius, and see if this relationship here makes sense. Is it going to really change by 2 millivolts per degree Celsius or not? So we expect an increase, so we can do the experiment and find out. Now for the diode, what I'm using an NPN device where I'm using the base emitter junction, and I have disconnected, I've cut off the wire that is the wire for the collector. This is a 2N222A type device, a very common NPN type transistor, and I'm only using the base emitter junction, which is a diode, so I can measure that. So I have connected the diode to the meter here. The multimeter right now is set to measure voltage, so you're not seeing anything. So here's the diode. I've connected it to the cables from above, and I'm going to change it to the diode mode, and I'm measuring 0.662 volts at room temperature. The Regal multimeter will put a constant 1 milliamp current through the device when the diode mode is selected. That's how I ensure that I have exactly 1 milliamp through the device at all temperatures, is because it's done by the instrument itself. So at room temperature I have 0.661 volt, so I'm going to write that down on our sheet. 0.661 volts. And now I can put this into the liquid nitrogen and see the change in the voltage across it. I expect an increase. So I think we've run out of, no, we still have some liquid nitrogen in there. Here we go. I'm putting it inside. And there it goes. now it's sitting in liquid nitrogen. You can see the voltage is rapidly went up. Now it's pretty much stable because the device is so small, so it doesn't take a long time for it to cool down, unlike the coil that we tested before. And the voltage is 1.053 volts. So if I take the difference between that and what we measured at room temperature, I'm using the calculator for that, 0.661, I get 392 millivolts. If I divide that by 2, it gives me approximately here. So I calculated, so we saw 0.661 volts at room temperature and 1.053 at liquid nitrogen minus 196. And if I divide that by 2 millivolts, I get 196. So based on this number, I was expecting something around a little bit more than what we measured, but it's very close. It's about 2 millivolts per degree Celsius. So the equations don't just predict the direction, but also very close to the value we expect. Again, the temperature range is so large that this 2 millivolts per degree Celsius may not be exactly valid for the entire change in the temperature, but it works quite well, and as a result, diodes have been used and are being used to measure temperature because their behavior is so well modeled. So we looked at the effect of temperature on a PN junction in an NPN device. So let's look at some MOSFETs and see how they change with temperature. One easy way to measure that is to look at the CMOS ring oscillator, which is nothing more than an odd number of CMOS inverters in a loop, which meets the Barkhausen's criteria for oscillation. So it will sustain a continuous oscillation, and you can get a square wave out of it. The frequency of oscillation is 1 over the period, don't mistake it with temperature, which is equal to 1 over 2n tau d, where n is the number of stages, number of inverters in a row, and tau d is the propagation delay through the inverter. The propagation delay through the inverter, which consists of an NMOS device and a PMOS device in this configuration, is 0.69 R equivalent times CL. R equivalent is the equivalent resistance of the NMOS PMOS devices as they go through all of their triode, saturation, and off regions of operation. And CL is the load capacitance that is driven by each of the inverter. So in this case, the load capacitance is the inverter's own capacitance and the capacitance of the next stage. Then R equivalent itself can be estimated using this equation, 2.5 divided by mu n C aux, W over L, VDD minus VTN. Let's take a closer look at this equation and see what it has. It has C aux, which is a technology parameter, W over L, which is the physical dimensions of the device, and once they're manufactured, that's fixed. VDD, which is what we apply to the circuit, we can keep that constant. And then it has the threshold voltage and the electron mobility. Both of these are a function of temperature. The threshold voltage will change, it will go down as the temperature goes down, and the mobility will go up as the temperature goes down because the electrons can move with greater ease through the material, so the mobility improves. So, as the temperature drops, the mobility improves, the threshold voltage drops, which means the R equivalent will get smaller because the denominator gets bigger. So R equivalent gets smaller, therefore the propagation delay will get smaller, and the frequency will then get higher. So you can see that from this relationship, if I were to cool the ring oscillator, I should be able to increase this frequency through this relationship between all the parameters that define the operation of the ring oscillator. So I'm going to cool it down and see the effect in the temperature. So I have built this circuit like this, and because again I have to build everything at the end of these sticks because the opening of the Dewar is so small and I will not be able to put anything inside it otherwise. So this is a hex inverter package. It has 6 CMOS inverters in it. I have connected 5 of them in a ring oscillator and the last one as an inverting buffer at the output, and I'm catching the output of the last inverter. You can see I've just created a loop with a bunch of wires around it. The red wire is VDD, the orange is ground, and the yellow is the output of the circuit itself. And all of that then goes through this and comes out as 3 wires which I can connect to the circuit. So what I've done here is that I have the oscilloscope, the Regal oscilloscope, turned on. I also have it displayed on this. So I'm going to connect it up so that you can see. Let me raise this a little bit so you can have a better idea. Like so. Here we go. So you should be able to see the output waveform once I connect it. And let me do that quickly. Make sure the power supply is turned off. Connecting the output to the oscilloscope. That's just noise that you're seeing right now. The power supply is connected to VDD and ground connection, and I'm connecting this to ground. There we go. So I'm going to turn the power supply on, and there's the waveform. So this is the sustained oscillation of the ring oscillator, and since the Rigol oscilloscope has a built-in frequency meter, a counter, I can see the frequency of oscillation here at 27.8 megahertz. I'm going to write that down on a piece of paper. And the signal swing is 6.62 volts peak to peak. The power supply is only 5 volts, and the waveform looks really unusual. The reason it looks bad, it has nothing to do with the ring oscillator itself. It has to do with the fact that the wire that I'm taking out of the ring oscillator, this long cable that comes out of the ring oscillator, which has the output taken out, that is just a wire with no shield and sitting right next to the ground, and it's this long wire which is quite inductive. And there are reflections that go back and forth on that wire due to electromagnetic laws and other type of impedance mismatches, which I'm not going to go into in this video. So this is why the waveform looks so bad. And this is the reason why we're having this, this shape. Let me make sure to separate these wires because they're shorting out. Okay, so now I'm going to put this directly inside liquid nitrogen, and then you should be able to see a change in the waveform shape and its frequency and its voltage. Okay, I'm about to insert the circuit into the Dewar. So have your eye out on the waveform, and here it goes. Look at the shape of the waveform and look at the frequency that it is oscillating at now. So there are several things that have changed significantly. The first is that the frequency went to 56 megahertz. It used to be 27, I believe, 27 megahertz, yes. So it's significantly higher. It more than doubled in frequency due to the drop in temperature because the devices became so much faster. But also the frequency changed. As a result, the output impedance is now important because it is now a different impedance at this frequency. So the signal swing changed. Also the devices became much faster, and they can switch much harder and much quicker, which increases the output swing even more. So right now the output swing has gone to 14.7 volts or so, which is significantly higher than it used to be. And here we go, maybe stabilize that a little bit. So I've actually done this experiment before, and I got as much as 15.8 volts peak to peak of output swing with using the same circuit when it's submerged in liquid nitrogen. So you can see a significant change in both in frequency and in the output swing, and I've written those down here. Get this guy out. Here it is. This is the measurements I did the first time I did this measurement. So we went from 27 megahertz, 19 milliamps of power consumption at 6 volts peak to peak, to 56 megahertz at 50 milliamp power consumption and 15.8 volts peak to peak of signal swing. So a huge change by dropping the temperature. But note that there is a difference between MOSFETs and bipolars. The bipolar devices also get faster, so I don't want to mislead you, but the junction voltage of a bipolar will actually go up as the temperature goes down. So if you build a circuit that consists of only bipolars and the temperature goes up, the circuit heats up, for example, its junction temperature will go down. But as soon as its junction temperature goes down, it will get more current. And if its current gets higher, then its temperature will go back higher, so it will get into what's called a thermal runaway. So you have to be very careful when designing circuits with bipolars to prevent thermal runaway. I have another little circuit that we can try frequency of oscillations with. Now this looks like an ordinary LED, except that it has two colors inside it, and there is a little CMOS circuit on the inside that is essentially an oscillator that goes back and forth between the two colors. So this thing flashes green and red back and forth at a constant steady rate, which is just above maybe a few hertz or so. But if I were to cool this LED down significantly, the circuit that's responsible for the oscillation will have to become much faster, just like the ring oscillator did. So the flashing should become much more quick. So I thought this would be a fun little thing to measure. So let me turn this light off so we can easier see it. Let me focus here. So there you go. You can see there is a lot of condensation on the outside, but that's still much better than if this was not a Dewar, because it would have been then completely frozen if this was not. So here you go, I turned it on. You can see that it flashes between the two colors. It's red and green. So I'm going to put it inside the Dewar. There you go, you can still see it flashing. This is still above the liquid nitrogen level, so it's still at room temperature. And I'm going to now put it inside the liquid nitrogen, and let's take a look at the frequency. There we go. There it is, and it goes absolutely insane. It was oscillating at just a few hertz. Now it's much faster. You can see in the camera. I can pull it back out, and it will warm up and it will slow down again. Bring it outside here. You can see how fast it's flashing. And I'm gonna hold it in my hand a little bit to warm it up. See, as it warms up more, it's gonna take some time for it to warm up. But you can see it's slowly warming up. There you go. It's becoming much slower. So let's look at some light emitting diodes. Or an LED. Now LEDs come in different colors. The most common are green and red, where green is between 500 and 570 nanometer is the wavelength, and red is between 610 and 760 nanometer. Now LEDs are made using materials that have a direct band gap. Now green and red are typically made from the same material. Indium gallium nitride or aluminum gallium indium phosphide are a type of semiconductor materials that are used to create LEDs. So you can get a different color by changing the band gap of the direct band gap of the semiconductor you're using. And lambda is given by hc over E, where c is the speed of light and h is Planck's constant and E is the band gap of the semiconductor. So E is a function of the material, but E is also a function of temperature. Typically in a semiconductor, if you reduce temperature, the band gap goes up. So you would expect that if I were to reduce the temperature of an LED, since the band gap energy goes up, you would have to have a shorter wavelength. So you would expect the green for the wavelength to become shorter and shift toward blue and not toward red. But when I did this experiment, I got a different result. So let's do this experiment and see what happens. So I've placed the LED inside the Dewar. There is no liquid nitrogen in there, and I've placed a little piece of paper at the very bottom in order for the light to reflect off of, so you can see the color better in camera. I waited for the Dewar to warm up so the condensation went away so you can see the color better. So here it is. You can see that it is a green LED. So let me turn some more of the lights off. There you go. Hopefully it's more clear. You can see the color. Now I will add some liquid nitrogen to the Dewar, which will cause the temperature to drop, of course, and then you can see what happens to the wavelength. Remember that I was expecting the wavelength to become shorter and the color to become more toward blue, but it seems like we're going to observe the opposite. So let's see. Here we go, a little bit. Now, I don't know if you can tell, you should be able to see that by now, that it became more orange. It's more yellow, and from my view, not through the camera, it's completely orange. The wavelength changed to become longer. It went from about 550 to closer to more like 600 and 610. So it is going in the opposite direction from what the theory predicted. If you go back to the piece of paper that I had written down the equations, this tells me that since the wavelength became longer, that means the energy, the E must have gotten, the band gap energy must have gotten smaller, so in fewer electron volts than it used to be. Now I'm going to write down what we observed. So at 25 degrees Celsius we saw green, and at negative 195 degrees Celsius we saw orange. So to be honest, I'm not 100% sure why this happens. It seems like at these very low temperatures some other factors start to kick in, and some other energy bands may be introduced that is responsible for creating this color. So I thought it would be a cool thing for us to discuss on the forum so that we can hear what other people have to say, and it would be an interesting topic of discussion. Well, I hope you enjoyed the experiments with liquid nitrogen. I have all of these components that I use for the experiment, and if you're interested in having these, I can send them to you. Just leave a comment and I'll pick one person and send you guys all of these ones that I use for the experiment, just in case you want to do your own similar experiment, maybe in the opposite direction, since really there is nothing else I can do with these. I will also put these results of the experiment. I'll kind of make a copy of them and make them available on the website, so you can look back and see what we got and what the theory was and what the equations were that describe the behavior of the circuit. So until next time, hopefully I have a chance to make some other videos and some other experiments. But if you have some suggestions, make sure you leave a comment and let me know, and rate the video so that other people can see them as well.